Welcome back to Pre-Calculus. We are here in Unit 9 and Lesson 6. Today's learning target is 9.c, which says calculate the dot product and cross product of two-dimensional vectors. So in our last learning target, we focused on the basic vector operations, such as adding two vectors or subtracting two vectors. And we also looked at what happens when you multiply a vector by a scalar. You multiply a vector by a normal number factor, like 4 or 1/2. What we haven't talked about yet is how you multiply one vector by another vector. And that's because there are actually two different types of vector multiplication called the dot product and the cross product. And they both are sort of like multiplication, but they have their own real-world applications and their own problem-solving process. And that's going to be the focus of today's lesson. So first off, a little bit of review about how we represent vectors. Vectors can be represented in really three different ways, and the first two of those are pretty familiar. That would be magnitude and direction, or component form. So for instance, we could talk about a vector in terms of how long it is and what direction it's pointing. So if I have an arrow that is 5 units long at an angle of 53.1 degrees. We could also represent the same vector in component form, where you think about how far over and how far up or down you have to go to reach the terminal point of that vector. So if this vector were started at the origin, so I put this not just anywhere in space, but right at the origin of the graph, then this terminal point would have the coordinates 3, 4. It's as if you went 3 units over and 4 units up to get to that terminal point. Now there is actually a third way of representing vectors, and that is in terms of unit vectors. And this is very similar to component form, but just written slightly differently. So unit vectors are vectors that have a magnitude of 1 and a direction along an axis. So the most common unit vectors that you would see would be I and J, and those are typically written, as you can see up here on the slide, with a little caret or a little hat over them instead of a normal dot. So that's how you know it's a unit vector instead of just a letter. So if you see them written with that little hat. So these are vectors that are 1 unit long, and the I unit vector is 1 unit straight along the x-axis. The J unit vector is 1 unit long straight along the y-axis. So when we think about component form being 3, 4, you could also think of that as being 3 times the I unit vector plus 4 times the J unit vector. So if I is 1 unit along the x-axis, and we do 3 of those, and then J is 1 unit along the y-axis, and we do 4 of those, 1, 2, 3, 4, that lands us at that terminal point 3, 4. And the reason we use unit vectors is that occasionally we have to deal in not just 2 but 3 dimensions. So some of you may be familiar with this already, some of you may not, but we're very used to dealing with an XY graph. So you have your I unit vector going along the x-axis, you have your J unit vector going along the y-axis. Now imagine you have a third axis. We are dealing in something that is 3D, not just flat on the page. Then you would have a third axis that is coming out of the page straight towards you. So we draw this as best we can here so that it sort of looks three-dimensional, but really you would imagine this z-axis as pointing straight up out of the page towards you. So if you take your pencil and stab the computer screen with it right at the origin, that would be your third axis or your z-axis. And we use the k unit vector to represent 1 unit along that z-axis. So 1 unit coming straight out of the page towards you rather than just flat along the 2D surface of the page. Now, why do we care about all of this? We will get into that when we talk about cross products. Cross products are actually three-dimensional, but we are going to start off with the dot product, which is the other form of vector multiplication. And the formula here is fairly simple. If we have two vectors, u and v, defined by their x and y components in standard form, then the dot product is written as u dot v with a nice big fat bullet in between there. It's equal to the product of the x components. So you multiply the x components, you multiply the y components, and then you add the two together. So multiply the x's, multiply the y's, add the two together. And the result is going to be a scalar. So when you dot product two vectors together, the answer is no longer just a vector, it is only a whole number. And what does the dot product mean or represent? It, in layman's terms, tells you the degree to which two vectors point in the same direction. So if you could imagine shining a flashlight down from one vector onto the other vector, then whatever the shadow of that first vector is, however much of this vector here is cast along the same line as the first one, that length gives you the dot product. So if the vectors are pointing in pretty much the same direction, you're going to have a big dot product. If the vectors are pointing perpendicular to each other, say you have one vector here and the other vector here, and you try to shine a light down on it, this one won't cast any shadow at all. So that would be a dot product of 0. These are not at all pointing in the same direction. So let's look at some examples here. We are given vectors u, v, w, and x, and we're asked to calculate each of the following dot products. So remember that the formula for two dot products, if we have vectors u and v, then the formula is that the dot product is equal to the product of the x components plus the product of the y components. So in this first case, we're actually being asked to dot product vector u by itself. So we're going to be doing 3, 1, dot product 3, 1. So we multiply the x components together, 3 times 3, and we multiply the y components together, 1 times 1, and we add those together. So 3 plus 3 plus 1 times 1 is 9 plus 1, or 10. U dot v, we are given, again, vector u is 3, 1. Vector v is -1, 3. So if we dot product those together, multiplying the x components, we've got 3 times 1. Add to that the product of the y components, 1 times -3. That is 3 plus -3, or 0. Vector u dot w would be 3, 1, dot product with -3, -1. So 3 times -3 gives us -9. I'll write this out though. So we've got 3 times -3. And we're adding to that 1 times -1, the product of the two y coordinates. So it gives us -9 plus -1, so -10. And then last we have u dot x. So this would be 3, 1, dot product 5, 2. So multiplying the x components, you've got 3 times 5. Add to that the product of the y components, 1 times 2. So that's 15 plus 2, or 17. So now let's graph these vectors and see if we can interpret some of these different dot products. Why is it that u dot u has a magnitude of 10, u dot w is -10, u dot v is 0, and u dot x is 17? So vector u is given as 3, 1 over 3 up 1. So that would be vector u. Vector v is -1, 3. So to the left 1, up 3. That would be vector v. W is given by -3, -1. So that ends up down there. And x is given by 5, 2. So over 5, up 2. So this would be vector x. So just remembering what the dot product means. The dot product is the degree to which the vectors point in the same direction. So when I did u dot u, that was the u vector multiplied by itself. So of course u points in the same direction as itself, and so you get a number that is much bigger than either of the components alone. So the components here are 3 and 1, but when you dot product it with itself, you get a value of 10. So we have a fairly large number here, showing that these do point in the same direction. When I dot product u and v, these are perpendicular vectors. They don't point in the same direction at all. If I were to shine a flashlight down onto vector u from vector v, it wouldn't cast any shadow at all. So these are not pointing at all in the same direction, and that is why the dot product is 0. When we compare vectors u and w, notice that they are pointing in the same angle, but in opposite directions. So they are basically the same vector, but negatives of each other. So when I combine those together, they're in the same direction, just as much as u and u were in the same direction, but because they're going towards opposite ends of the ray, that's why we have that -10 in there. So they're on the same angle trajectory, but one is going the opposite direction as the other, and that's what makes the dot product negative. And the last one that we look at is comparing vectors u and x. So again, this is vector u, and this is vector x. And they are pointing in pretty much exactly the same direction. Not quite on top of each other, but very close. And notice that x is quite a bit longer than vector u. So when we take into account the fact that they are pointing in almost the same direction, and also the length or magnitude of the vectors, that gives us the biggest dot product of them all. So the only thing you need to do with a dot product is be able to calculate it, but it's good to kind of mentally check, does it make sense? The bigger the dot product, the longer the vectors should be, and the more they should be pointing in the same direction. If the dot product is something very close to 0, it means they're nearly perpendicular to each other. And if the dot product is negative, that means they're along the same angle line, but going in opposite directions. So that's the dot product, which is the first type of vector multiplication. Now let's look at the cross product. And this one is a little bit more complex. So if we have two vectors, so again, we'll call them u and v. They're defined in standard form by their x and their y components. Then the cross product, we use this with a big X multiplication sign, is equal to the x component from u times the y component from v minus the x component from v times the y component of u. This is easier to visualize if you write them out on top of each other. So you have vector u with its x component and its y component. And then underneath that you have vector v with its x component and its y component. So the cross product is the product of these two numbers minus the product of these two numbers. So you go in kind of an X shape. You multiply u sub x times v sub y, and then you subtract from that v sub x times u sub y. So it's a crisscross shape cross product shape. So that's how you get the magnitude. Notice that we also have this n tacked on at the end. And that is because the result is a vector that is perpendicular to both vectors being multiplied. So if you have x components and y components, then your resultant vector will be a z vector, one that is coming out of the page in three-dimensional space, perpendicular to both your x and your y. If you had some sort of weird two-dimensional vector that had x and z components, then the cross product would be in the y direction, perpendicular to both of the ones that you were given. So what does this mean? The length of the cross product vector is equivalent to the area of a parallelogram formed by the two original vectors. So if I have two original vectors, A and B, and I use those to draw out a parallelogram, then the area that parallelogram takes up, the amount of space that we have there, is equivalent to the length of the cross product vector. So it's not a super intuitive definition, but that is what the cross product represents. Mostly you just need to be able to calculate it. Crisscross applesauce, u sub x times v sub y minus v sub x times u sub y. And remember that the result is a vector. So you have to tack on an I, a j, or a k, some kind of unit vector there at the end to show that you know your result is a vector and not just a scalar. So we'll use the same u, v, w, and x vectors as we did before, but now we are going to practice calculating cross products. So the first one we'll do is vector u crossed with itself. So vector u is 3, 1, and we are cross producting that with vector u, again 3, 1. So remember that you are going in a crisscross shape. We are going to multiply across the diagonal, then subtract, and then multiply across the other diagonal. So this will be 3 times 1 minus 3 times 1. So in other words, 3 minus 3, or 0. So a vector cross producted with itself will be 0. Now let's do vector u cross v. So in this case we have 3, 1 and negative 1, 3. So if we cross product those, we are doing 3 times 3 minus negative 1 times 1. So we're doing 3 times 3 minus negative 1 times 1. So that's 9 plus 1, or 10. And now don't forget that this is not just a scalar 10. The result of a cross product is a vector. So if these two vectors that were given here have x and y components, which they do, this ordered pair represents x and y, then the resultant vector will be 10 units in the z dimension, so coming out of the page. So we can represent that using a unit vector k. So this would be 10 units along the z-axis. Or if you wanted to write it in standard form, we would have 0x and 0y and 10 units along the z-axis. So either of these would be correct ways of representing it, showing that you recognize that your answer is a vector and that is perpendicular to both of the vectors that you started with. Another example here, we have u cross w. So this would be 3, 1 cross producted with negative 3, negative 1. So when we go our crisscross applesauce, it'll be 3 times negative 1 minus negative 3 times 1. So we'll do 3 times negative 1 minus negative 3 times 1. So that becomes negative 3 plus 3. This is another one where the cross product is 0. And lastly, we have u cross x. So this is 3, 1 cross producted with 5, 2. So we do 3 times 2 minus 5 times 1. So that is 6 minus 5, which is equal to 1, and not just a scalar 1, but 1 unit along the z-axis. So either 1 times the unit vector k, or if you want an ordered triplet, no x, no y's, and just 1 unit along the z-axis. So whenever you have an actual answer for your cross product, you need to write it in vector form, either using a unit vector or an ordered triplet. So now let's make sure this all makes sense graphically. If we do u cross u, this first problem that we did, and we ended up with a value of 0, well, if I do vector u right there and vector u again, those don't make a parallelogram. So if the cross product represents the area of the parallelogram, there isn't one. So that makes sense. If we do vector u cross vector v, however, vector u is there, vector v is -1 up 3, so that is here. That one would make a parallelogram. So if I fill in the extra side, that would look something like this. And this tells me that this parallelogram has an area of 10 units. If I do u cross w, we've already got vector u drawn in. Vector w is going in the opposite direction. So again, these are all on a straight line. So there is no parallelogram there. There is no shape that I could fill in to get an area. So that's why the cross product is 0. And lastly, if I do u cross x, so vector u is already drawn in, x is over 5 up 2, so that would be right there. So I could make a parallelogram here, but this would be a very skinny and flat parallelogram, like a diamond shape that has been squashed flat. It would look something like that. And so the area of this parallelogram is a very small amount of space, and that's why the dot product, or excuse me, the cross product only has a magnitude of 1. So that's how to calculate two different types of vector multiplication, either the dot product or the cross product. Now we want to do a little bit more practice with this, whether or not the vector is defined in component form, like vectors p and q are here, or whether it's defined in terms of initial and terminal points. We also want to be sure that you can combine this with other operations. Instead of just having p dot q, what if you had to do 3p dot 5q? So you can go ahead and pause the video here, try these ones on your own, but then hit play to see my work and talk through it. And here are your solutions. The first two on the left side are basic dot and cross products. So for the dot product, you multiply the two x components together. So you do 8 times 5 and add to that the product of -1 and 2, and you end up with a whole number 38. For the cross product, you multiply across the first diagonal 5 times -1, and you subtract from that the product of the second diagonal, 8 times 2, and you end up with a vector that has magnitude of -21 and direction along the z-axis. So don't forget, you do have to indicate the directionality using a unit vector here, or you could write your answer as 0, 0, -21. Either of those would be correct, but you do need to show that this is a vector. -21 on its own would not be considered correct. Now for these next two, you have to deal with some multiplication before you can actually do the dot or the cross product. So 3 times vector p would be 3 times 8 and 3 times -1. So we've got 24 -3. And then we've got 5 times vector q. So we do 5 times 5 and get 25, 5 times 2 and get 10. And then you can do the dot product where you multiply the x components and then you multiply the y components and add them together, and you get 570. And the reason this dot product is so much bigger than the dot product of just p and q alone is because we have significantly stretched out the lengths. So instead of having just one vector p, we've got 3 times as long, and vector q is 5 times as long. So the product of the two, the degree to which they point in the same direction, is magnified by their increased length. Now for p cross -q, vector p has not changed. It's still 8 and -1. But now instead of just plugging in vector q, we plug in the negative of that. So instead of 5, 2, we need -q, so -5, -2. And then when you calculate the cross product, 8 times -2 minus -5 times -1, that's a lot of negatives in there, but it comes down to -21 units along the z-axis, so -21 times the unit vector k, or no x coordinate, no y coordinate, everything is on the z-axis, 21 units straight down through the computer screen and out behind you. So we've got 2 more examples here, and these last 2 problems are not given to you in standard form. So instead of knowing right off the bat what your x and your y components are, kind of like we did in our last video for Learning Target 9B, the first thing you need to do is find the standard form version of these vectors. So remember that the standard form is always the difference between the final point and the initial point. So when you are finding out the standard form or the component form of, say, vector AB, you're going to be doing B minus A, -1 minus -5, and -4 minus 0. So the first step would be to convert all 4 of these vectors, A, B, C to D, A to C, and B to D, convert those all into standard form, and then you can calculate your dot or your cross product. So go ahead and pause the video here, see if you can figure those out, and then hit play to see my work. And here are your solutions. So I came up with vector AB in component form being 4, -4, and vector CD being 6, 3. Then if you dot product those two, you multiply the x components 4 times 6, you multiply the y components -4 times 3, add them together, and you get a scalar answer of 12. For vector AC, I ended up with 2, -1. For vector BD, it was 4, 6. And so when you cross product those, you're doing 2 times 6 minus 4 times -1. And that ends up with a magnitude of 16. But remembering that your answer does need to be a vector, not just the number 16. It is 16k, or 0, 0, 16. So that is it for today's learning target. You now know how to do both types of vector multiplication, multiplying one vector by another using the dot product or the cross product.